Hi, welcome back. And now we are going to discuss limitations or problems with RNN. So far, we discussed about the advantages of RNN that it can process sequential data, it maintains a memory which stores the previous output. So every time you calculate HT, whenever we calculate HT, we are calculating it as a function of the present input xt and also as the function of previous input. That means your ht is dependent on your present input as well as previous output. Of course, the remaining things are. So this is it is maintaining a memory to remember the previous things. But the problem is when you have long sentences. For example, here you have H1 coming in, then H2 coming in, H3, then you have some H100. So by the time you reach H100, remembering H1 is entirely difficult. It is very difficult. So even in your class, if you try to remember what happened in the first hour, in the last period, then it will be very difficult. So this first problem that we'll be dealing with is known as long-term dependencies. Long-term dependence. That means as the time progresses, remembering previous things is very, very difficult. Let me give you an example. Suppose I'm talking about a word prediction problem. Word prediction problem. What is the next word? So if my word prediction problem, suppose if I say Hyderabad is famous for, so immediately that word predicted, because it remembers Hyderabad very well, it come up with something like biryani. But you have a long sentence. For example, you started with Hyderabad. Let me present you this sentence. So did you see this sentence here? Hyderabad, a bustling city known for its rich history and technology hubs, has over the years became a melting pot of diverse cultures where people across the country come to work in the rapidly growing IT sector, discussing innovations and crowded lane Charminar, and finally their day savoring its all world famous dash 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 dash. So actually, my intention is it should predict the biryani there, but the problem is that it will predict biryani only if it remembers Hyderabad. That is okay when you have short sentence, but when we have long sentences, predicting that is very difficult. This problem we call it as long-term dependency. That means your prediction will be dependent only on the recent outputs, but not on the outputs which are obtained long back. This type of problem is also known as vanishing gradient problem. Vanishing gradient problem. If you remember the last class, we talked about the back propagation through time, and there we have discussed about how that error gradient is calculated. For example, dou E by dou W, we calculated it as, you can check that out in the previous video. I will just straight away write dou Y cap, and dou Y cap depends on dou H3 and dou H3 depends on dou H2 and dou H2 depends on dou H1 and dou H1 depends on dou W. This was the last term, and the third term for that three input words, that was dou H3 fine depending on dou H2 and dou H2 depending on dou W. Yes. So if you remember, this was the equation we derived or we have written. So from this equation, it is very evident that when you have long terms, long gradient, so this is your recent one and this is your old one, then it is very difficult to compute these things. Now look at, now this is the 3-word gradient. Suppose you have 100-word architecture, 100-word architecture. So what will be the that longest term? Dou E by dou Y cap, dou Y cap by dou H100, then dou H100 by dou H99, dou H99 by dou H98, so on, dou H2 by dou H1 into dou H1 by dou W. So this term is this term is a long multiplication. So this dou H100 by dou 99, dou H99 into dou H99 into dou H98, so on, dou H1, dou H2 by dou H1 can be written as a product of T. It is, let us say, 100 to 1 or 1 to 100. It is a multiplication of dou T by dou T minus 1, dou T minus 1. So what actually, how do we calculate this H? What is this H contains? What is the equation for HT? HT, if we have activation function tan H and vector U and xt plus that bias plus weight vector W into HT minus. So when you derive it, when you differentiate it, dou HT by something dou HT minus 1, this is the derivative of tan H derivative of tan h into, these are constants. So, and here dou ht minus 1 derivative with respect to dou ht minus 1 is 1 and into w. Now, when you have this one, this value is between minus 1 and 1, and you can take it is less than 1 because tan h range is minus 1 to 1. And generally, weights will also be between 0 and 1. You suppose I have a word something like this 0.123. If you go on multiply with the points 0.123, 0.124, 0.247, this something like zero point 0.1 to the power of 100. So it will be something like 0.000000000, so on. That means your gradient is vanishing. Your gradient is vanishing. It is becoming infinitesimally small. This is what we call vanishing gradient problem. So this because that means your prediction or your output y cap depends only on the previous h100 but not on h1. This is long-term dependencies problem or vanishing gradient problem. So the solutions to this problem is number one, because we have used this tan h, it is always between minus 1 and 1. So instead of that, we can change activation function and make it ReLU. What will ReLU will do? ReLU will give you the actual value. If it is greater than 0, it will give the same value. If it is less than 0, it will give the 0. So you can change the ReLU from tan h to ReLU. Of course, it has also some problem. We'll see shortly. And secondly, the weight initialization, because generally we start with 0, so we can use reinitialize the weights. That is another strategy. And you can also go for batch propagation, batch normalization, sorry, batch normal. That is another strategy to counter vanishing gradient problem. Then we can also change architectural aspects and we can go for skip RNN that we will discuss in the later skip RNN. Then fifthly, we can use alternative architectures like LSTM or GRU, gated recurrent units, which we'll discuss in the next class. So what is the first problem? First problem is vanishing gradient problem, which is also called long-term dependencies problem. That means your output is depending on the recent input, not on the last input. That is the first case. The second case is known as exploding gradient problem. Exploding gradient problem. That is the reverse of it. Your prediction will depend mostly on the long back inputs rather than on the present outputs. Why that will happen? For example, if you have ReLU here instead of tan h, you have ReLU here. So it will be more than 1, let us say. And if you multiply all the terms of more than 1, more than 1, more than 1, and with your weights are also more than 1, that will become explosive word. So it will be dominating the recent outputs. So this is known as exploding gradient problem. That means your output prediction is influenced by long term gradient rather than recent gradient. This is also a big problem. Here also what we can do, we can change our activation function from regu to again back tan H. Another strategy that we can use is gradient clipping. The solution to that is gradient clipping. What we do is to cut this gradient uh, so that it will not explode, is we will fix a value for gradient. And once we fix the value, then the gradient will remain in particular range. So these two are the major problems with RNN, though they are expected to be effective with sequential data. So because to address these things, we have alternate architectures. One is LSTM, long short-term memory. Another is graded recurrent unit, which we will see in the coming lectures.